Hello, I'm going to talk about a random greedy algorithm for producing a maximal independent set and how to analyzing it using local limits. And this is based on joint work with Michaeli, Krivelevich, Tamás, Mészáros, and Clara, Shikhelman. Let me start by a two example. Suppose we have a circular parking lot and cars arrive at the parking lot one at a time, parking at arbitrary spots. And assume the parking is discrete, namely each car occupies two consecutive curbs, let's say. And cars cannot overlap, they really have to find an available slot. And they keep coming until no more room is left. And the question is, how many cars have parked at the end of this process? And the answer clearly depends on the particular choices the cars have made when deciding where to park. So instead of asking about the best case scenario or the worst case scenario, I will be focusing on a typical scenario, that is when cars made their choices uniformly at random. We will shortly be able to answer this question, but just before it, let me phrase it in graph theoretic terms. What we're really interested in is the size of a typical maximal independent set, which was produced in a random greedy fashion. So here are some definitions. An independent set is a set of vertices, no two of which are adjacent. Finding a maximum independent set is notoriously hard, it's NP hard, and even hard to approximate. But finding a maximal independent set with respect to inclusion is very easy. How easy? It can be produced in a greedy fashion. By that I mean, given an arbitrary order of the vertices, we consider the vertices sequentially one by one according to this ordering, and we add them to our set or color them red if the resulting set does not span an edge. So 1 will be in our set, 2 will not be, 3 will be, and so on. So the resulting set will be maximal, but how large will it be? Well, this clearly depends on the ordering of the vertices. Here's an extreme example. If on the start, the first vertex we consider is the root, then the root will end up in the independent set, hence none of the leaves will be in the independent set, and the maximal independent set that we obtain will be very small. If on the other hand, the first vertex we consider is a leaf, then the root will not be in the independent set, hence all leaves will be. So we will get a maximum independent set. But which situation is more typical? Well, at least if the star is large and the first vertex we consider is picked uniformly at random, then the situation to the right is much more probable. So it does make sense to replace an arbitrary ordering by a random or uniform random ordering of the vertices. But given the ordering, the algorithm runs just the same. We add a vertex to our set as long as the resulting set does not span an edge. So again, we obtain a maximal independent set. And I'll just mention that this maximal independent set we obtain is just the first color in a random greedy coloring of the graph, which colors vertices one by one according to this random ordering at the first available color. Okay, let us denote by I the yielded independent set and by iota its density, which we call the greedy independence ratio. Note that this is a random variable, even if the base graph is deterministic, just because the randomness comes from the ordering of the vertices. And people have been studying this quantity for at least 8 years now, perhaps started by Flory, who was an American chemistry Nobelist, and later by Page, a British computer scientist who studied it for the line, showing that this converges to this number here. And later on, combinatorialists have studied it for various random graph models, like Diamond for the binomial random graph with linear edge density, Wormel for the random regular graph, later extended it with Lauer for deterministic irregular graphs with exploding Earth. Quite recently, two distinct groups, Brightwell, Jansson, and Luchak, and independently Bermol and Jonker and Royal, have studied it for uniformly chosen random graphs with a given decay sequence. Before discussing our contribution, let me just give yet another equivalent formulation of the model. Given random or arbitrary ordering of the vertices, instead of considering the vertices sequentially, we can compute the maximal independent set in parallel as follows. At time 0, every vertex is active. And at each round, every active vertex look at its active neighborhood and see whether it has the lowest label, in which case we call it a sink, and it colors itself red. If on the other hand, it has a red neighbor, it deactivates itself, and we continue to the next round. Now 8 is a sink, so we color itself red. Quite recently, Fisher and Weber showed that this algorithm terminates in at most logarithmic number of steps, and this is tight. And in this sense, at least, the algorithm is also very efficient. But note that we did have one global step here, so it's not really local in the sense that we need to determine an ordering of the vertices, random or arbitrary. We could have easily avoided it by settling for random ordering by letting each vertex choose its own label. Just pick a number between 0 and 1, uniformly at random. And this random labeling induces a uniform random permutation on which we can run the algorithm just as described earlier. So we get exactly the same independent set. And in this sense, the algorithm is very local. For example, to determine whether this guy here is red or not, we did not need to read the value here, for example. And to determine whether this guy is red or not, we did not need to read the value here, and so on. An advantage of this is that we can apply this algorithm in this formulation for infinite graphs. Well, not always. For example, if on the bi-infinite path we have sampled by chance a monotone increasing path, then there will be no sinks and the algorithm will not run. But this will never happen. So here's a more typical situation. Suppose now that I want to determine whether this guy here is red or not. So I don't need to read infinitely many values. Instead, only finitely many values. So how many? I just read values on vertices which are obtainable by a monotone decreasing path, plus the boundary vertices, just to know that the decreasing path has ended. So now to determine whether this guy is red or not, I run the greedy algorithm on this finite subset of vertices. So these will be sinks. These are neighbors of sinks. This is a sink now, and this is a neighbor of a sink. So our guy will not end up red. But why would I want to apply this algorithm for infinite graphs? Well, I hope that this will be motivated now. The next slide, in which I describe our general framework. We are given a graph sequence with order tending to infinity, and we wish to calculate the asymptotics of these random variables, the greedy independence ratios. So we start by estimating their mean, observing that this mean is just a probability that a uniformly selected vertex will end up red. And we hope that this will be determined by small neighborhoods of these random vertices, since we will be able to deduce a decay of correlation phenomena from which in turn we will be able to show that these random variables are concentrated about their mean. And we head on to analyze this local view of random vertex. And this is captured by a very nice notion of a local limit or Benjamini-Schramm limit, which is usually a random rooted infinite graph. And we reduce our question to calculate the probability that the root in this random rooted infinite object is red. At least in some cases, we are able to develop machinery to calculate that probability. Okay, so what is a local limit? We say that a graph sequence converges locally to a rooted graph if for every fixed radius, the ball of radius r around a uniformly selected vertex in the graph sequence converges in distribution to the ball of radius r in the limit. Which just means that for every fixed ball, the probability of seeing it around the uniform vertex in the graph sequence converges to the probability of seeing it around the root in the limit. So this is really convergence in L1 of the probability mass function. So here's an example. Let us consider the sequence of cycles. And for every fixed radius, if the cycle is long enough, then from every vertex, looking at radius r, I don't see the cycle closes. So what I really see is a path that goes r in both directions. So the local limit in this case will be just a bi-infinite path, rooted somewhere. But it need not be deterministic. For example, if our graph sequence is the sequence of binomial random graphs with linear edge density, then the local limit is the Galton-Watson-Poisson tree. And if our sequence is the uniform random labeled trees on n vertices, then they convert locally to a size-biased version of this Galton-Watson-Poisson tree, which I will define later. But even if the graph sequence is not random, the local limit may be random just due to the randomness in picking the root, the uniform vertex. Okay, so these are local limits. Here are our theorem. We assume that our graph sequence has subfactorial path growth, just a very weak growth assumption, strictly weaker than bounded degree assumption, which implies exponential path growth. Given this assumption, if our graph sequence has a local limit, then the sequence of greedy independence ratios converges asymptotically almost surely to this number, which I denote by iota of u, which is the probability the root is red in the limit. So this is really two theorems coupled together. One theorem is about convergence of the means of these random variables to this number here. And one theorem is about concentration of these random variables about their mean And here we don't really need local convergence, just a growth assumption. And this was observed by Gamarnik and Goldberg roughly 10 years ago for the bounded degree case. So we extend it to strictly weaker assumptions and give a different proof. And our proof for concentration is somewhat based on the following exploration algorithms lemma, which more or less states the following. I want to determine the value of some Boolean function, say it's two distinct sets, points in my graph, and I know that the value will be determined by some random local neighborhood. So if I know that the radius of these random local neighborhoods are typically much smaller than the typical distance between the points that I want to calculate the Boolean function on, then the Boolean function's values will be very uncorrelated. And this will give me concentration. Okay, so we have a goal. We now have to calculate that the probability that the root is read in some random rooted infinite graph. But this might be very difficult. For example, even for the two-dimensional lattice, this is widely open for at least 60 years now. So no one knows what is the probability that the origin, say, is going to end up read in a random greedy coloring of the two-dimensional lattice, for example. And really, the difficulty here is the existence of cycles. So instead, we will be focusing now on locally tree-like graph sequences, namely graph sequences for which the local limit is almost surely a tree. And with trees, the situation is much easier, since the root of a tree is going to end up read if and only if none of its children is going to be read. And at least when the subtrees that I see here are independent of each other, so either they are deterministic or they are random but independent, then conditioning on the label of the root, if I only look at the children of the past, children with label less than the label of the root, then they will be roots to independent sub-processes. So the entire picture I see here, for example, and the entire picture I see here will be independent. If all of these trees, the subtrees and the tree itself, have the same law, then we call it a single type branching process. And then we get some quite easy recursion. And if they have several laws, then we get a multi-type branching process, and then still we can say something. So here's the recursion for a single type branching process. We denote by y of x the probability that the root is read and that its label is less than x. So we're really after y of 1. And we can write it as the following integral. And taking a derivative, we see that y prime of x is just the probability that the root is read, given that its label is exactly x. And this will give us the following recursion. Y prime of x is just the average over the number of children times, for each of the children, I need it to be not read, conditioning on being in the past, which is what's in here. And this, the product here is because of independence of the different sub-processes that I see. And we have a boundary conditions, y of 0 equals 0, just from the definition of y. For a multi-type branching process, I need to add types. Just observe that in this case, instead of an ODE, we get a system of ODEs whose size is just the number of types. So this all might seem very complicated, but here an easy example, solving at least asymptotically the question from the first slide. We know already that the paths and cycles converge locally to the bi-infinite path, and we can think of the bi-infinite path as a two-type branching process as follows. One type is the roots type. It has two children of a branch type, and each branch type node has one child of a branch type. So for branch type nodes, in order for a node not to be read, it needs its only child not to be both read and in the past, and we can solve this recursion differential equation. And for a root type to be read, we need its two children, which are of branch type, independently not to be read and in the past. And we can solve this as well, plugging in x equals 1, we get the result of Florian page. But we get a bit more, we get this time evolution bonus here. So for example, if I plug in any other x than 1, then I get the density of this set. It's time x when ignoring every vertex whose label is more than x. And this number here is just a little bit less than a half, which is the independence ratio of the path in the cycle asymptotically. Knowing the easy fact that the binomial random graph with average degree d converges locally to the Poisson d branching process, the one line calculation gives us the result of McDiarmid, and with the time evolution bonus. So we know what happens at time x as well. And this is, at least for d large, half optimal. And this is not a coincidence. It was shown by Rahman and Virag that this kind of local algorithms are always at most half optimal. And in this sense, the greedy algorithm is as good as it gets. A very nice result by Krivelevich shows that a uniform random tree on n vertices labeled converges locally to a size-biased Galton-Watson-Poisson tree, which can be described as follows. First, we put an infinite line, and then on each vertex, we grow independent Galton-Watson-Poisson tree, which is almost surely finite. So the ball of radius R around the uniform selected vertex in a random tree converges in distribution to the ball of radius R around the limit in this tree. And this is really a two-type branching process, one type for the spine vertices and one type for the vertices on the trees. So for the vertices on the trees, we've already solved the recursion. And for a spine vertex to be read, it's needed its only spine vertex child not to be read and in the past. And it also has to be read as the root of Galton-Watson-Poisson 1. Plugging in 1, we get 1/2, which is just below the independence ratio of random trees as found by Meir and Moon in the 70s. And we've run a simulation just to make sure that everything works. Indeed, this is a random greedy coloring of a 250 vertex random tree, and exactly 125 are read. Simulations don't lie, but of course I do because I carefully chose this simulation. But my point is that really even for this small number of vertices, this greedy independence ratio is very tight, very concentrated. Let me sum up our results. We have the result of Flow and Page. We have the result of McDiarmid with a neat probability generating function trick that allows us to kind of skip solving complicated ODs. We have the result of Wormald. By noticing that D-regular graphs with exploding Earth have the same local limit as a random regular graph, just the regular tree. We have the result of Lauer and Wormald as well. We have a new result about uniform spanning random trees, which can be applied for random functional digraphs or one-out graphs, which have the same local limit. Okay, as a bonus result, recall that the greedy independence ratio of the path converges to this number here, which is just below 1/2, and the greedy independence ratio of the star converges to 1 because we typically start by a leaf. Are these lower and upper bounds for trees? So this is what we wanted to show. We wanted to show that asymptotically, if you take the random greedy maximal dependence set on any tree, you will get something which is at least as large in excitation than on the path. It was a bit difficult to prove it using the tools that I've described earlier because, for example, the stars don't have a local limit. But instead, we were able to find a non-asymptotic version of this theorem, like an exact version, which states the following. For every fixed number of vertices, the expected size of the greedy maximal dependence set on any tree will be at least as large as that on a path with the same number of vertices. And for this, we needed a more combinatorial approach and combinatorial tools. And we would like to kind of, there are many open questions in this kind of sub-question. So let me finish by some open questions. The first most interesting question is how do we analyze the random greedy, the greedy independence ratio on infinite graphs which have cycles, for example, the lattice. As I said, this is widely open for at least 60 years now. And there are some bounds, but nothing which allows us to solve it in any known case. And there are some better or different local rules for producing a maximal independence set. There are some other optimization problems which are not related necessarily to independence sets, which can be, for which these phenomena, these kind of tools can be applied for, but we have not done it. And our tools allow us to calculate, for example, the expected size of the second or the third color. But can we say something smart about it? For example, is it true that if we combine the first two colors on any tree, then in the path, it will have the smallest expected size, which will not be true for 3 colors because 3 colors will be enough to color the entire path. And it won't be the situation in any graph, of course. Okay, so I'll finish here. Thank you very much for listening.